Good afternoon, everyone. My name is Carol Werner. I'm the Executive Director of the Environmental and Energy Study Institute. Transmission and how the grid works is a major concern. It is also an area that requires great investment, and indeed the grid is worth billions and billions and billions of dollars. And how we make the grid more reliable, more resilient, how it really works, what are the different roles in terms of federal as opposed to state policy making in terms of thinking about the rules. How do all of these things interplay? We're going to hear about all of that from a very distinguished faculty this afternoon. And in fact, probably by the end of this briefing, and of course we will take questions at the end after you've heard the presentations and kind of the walkthrough of the different components, you will probably feel that you should be receiving continuing education requirements. So we look forward to these presentations this afternoon. I think it's a great opportunity to really have a much better understanding of how this really critical grid transmission system works, and in terms of each component, and as it brings power to our whole economy, wherever we are in terms of our homes, our businesses, how we basically do everything in this economy. It's really critical to have a better understanding so that we can all figure out how to have smarter, sound policy to address it. So I am now pleased to introduce the moderator for this afternoon's briefing, who is Jim Hecker. Jim is the counsel to WIRES. He is at Husch-Blackwell. And of course, he is a former chairman of FERC, the Federal Energy Regulatory Commission. So there's nobody better to help lead us through this. Jim?
Well, thank you all for coming. I don't know if there's someone better to lead this, but I have the job. So I think we're going to have a pretty intense little educational experience. You know, why is transmission important? You know, when we started the WIRES group, it was hard to find people who were very interested in the grid or in infrastructure generally. But I'm finding that in policy circles, in industry circles, political circles, talking about infrastructure, America's infrastructure, and how we build a stronger economy, provide jobs, all those things resonate with policymakers. And there's no more important piece of our infrastructure than the electric transmission grid. I should explain to begin with that this is sponsored by WIRES, and you can find a lot of information about transmission on our website, www.wiresgroup.com. And it's a very newsy website, but it also has some important studies and other information on it. WIRES has done, probably we're about a dozen of these briefings on Capitol Hill over the last 3 Congresses, and we're delighted that you found time today to join us. And I want to thank Carol Werner and EESI for helping us organize it. WIRES is a national group of companies, co-ops, municipals, investor-owned utilities, consultants, various people, renewable energy developers, people who are interested in ensuring that we all understand the need for investment in the electric transmission system. It's a system that is critically important. National Geographic did an article on the grid, almost like a force of nature, about a year or 2 ago. And they said we're all embedded in the grid because we depend so heavily on electricity to do almost everything in our daily lives. So electric transmission, the adequacy of that system is essential for our standard of living. That's not an overstatement. That doesn't mean that in the energy sphere, the transmission is the solution to all problems. I think it's important to consider energy efficiency, demand response. I think it's important to look at alternative sources of energy and microgrids. And we have a lot of technology heading at us right now. But we are going to be a networked society, a society that depends on the grid for the foreseeable future. The problem with that is that a lot of the grid is 40 and 50 years old. It's electromechanical. It's starting to be digital. It's congested in many places, which keeps electricity prices high. It is inadequate to connect the rich sources of renewable energy that we find offshore and in the middle of the country. We need to invest in upgrading to digital technologies. And it's vulnerable. Superstorm Sandy was a good demonstration of how we need a more resilient grid. But if you ask the American Society for Civil Engineers how good the electric transmission system is, they give it a D+. They are very afraid that we're going to underinvest in the grid over the next couple of decades. Our economists that we've spent a good deal of time with, project that the country's going to have to spend $300 billion with a B dollars over the next 20 years to accommodate the new technologies, the new fuel mix, the demands for more reliable electricity. And most of that money will not come from government, it will come from private sources. So regulation is extremely important. You're going to hear today, we call it Transmission 101, because we're going to march through a whole bunch of really important issues, starting out with what's a kilowatt. But hang in there, because this information, if you're interested in electricity, is going to be really important, and I think you're going to have this to take home with you. So the faculty, as Carol puts it, is for people who have done things like this before, and the latest being this morning at the Department of Agriculture. And we think that there's a really compelling story to tell about what the grid is, how it operates, who regulates it, and who ensures that it stays reliable even under adverse conditions. Our first presenter is Wayne Galley. Wayne is currently working for Clean Line Energy. He's an engineer, but he's been around a long time. He's worked for NextEra Energy, for the Southwest Power Pool. Clean Line develops high voltage direct current transmission, and you're going to hear the difference between direct current transmission and alternating current transmission from him, as well as a lot of other very basic facts about grid operations. Secondly, Jeff Dennis, who's the director of the Division of Policy Development at FERC, within the Energy Innovation Policy Division. And he's a former assistant to Commissioner Norris. Jeff is going to talk a lot about what's happening at the FERC and the implications of what it's doing. Third, Jay Casberry. Jay is Director of Research and Development and Special Studies at the Southwest Power Pool. Jay has a long history in the industry as well, and has been working at SPP, I think, for 10 years or more. Jay has also been a detail to the Department of Energy to help them with their grid tech projects and other transmission planning projects. And last, but perhaps very importantly, is David Cook. Dave is an old friend of mine. He was a lawyer at the FERC. He was Deputy General Counsel there and worked there in various capacities for 20 years. Went on to be General Counsel of the North American Electric Reliability Corporation, which is the designated national, or North American really, reliability standard setting group. I can't think of anyone who understands this business better. We are excited to be here, and we'll try to get through this material and give you all time to ask questions. I think our emails are at the end of the document, so you're more than welcome to pursue us afterwards as well. So we're going to start off with Wayne, and we call him Professor Galley.
Thank you, Jim. For those, just for your information, I am standing, so those in the back can't see me over the podium. I apologize. Got the right button there. Well, again, thanks for coming and taking time out of your schedules to learn a little bit about electric transmission. For some of you, the material I'm going to cover is pretty basic and pedestrian. For others, it might be the first time you've seen it since freshman high school physical science. But we're going to keep it go at a pretty steady pace because I think the goals here are to try to cram into 20 minutes or less an understanding of the complexities of the electric power grid. And the grid is arguably, in my mind, one of the largest, most complex machines that man has ever constructed. From an engineering perspective, it's extremely exciting. As an electrical engineer by training and profession, it's exciting because it's got almost every aspect of electrical engineering involved in it, from electromagnetic fields to circuit analysis to computer controls, to communications, the whole gamut of electrical engineering. And so on top of that, from an engineering perspective, it's got mechanical engineering, chemical, civil. So it really spans the gamut, and it's a fascinating machine. It doesn't have the sexy allure of nanoelectronics, perhaps, but it's fundamental to our daily lives, as Jim has pointed out, and extremely important. So it's got a lot of neat, geeky engineering aspects to it. But since it's a fundamental element of supplying energy, it also has plenty of meat for policy wonks to sink their teeth into. And we'll find out if you go further, what you start to find out is that a lot of times physics and policy don't often match up, and therein we have some pretty interesting engineering problems to tackle. Sometimes when policymakers don't understand physics and engineers don't understand policy. So hopefully we'll help bridge some of that gap. So in general, basic definitions, voltage and current, you've all heard of these. Voltage you can tend to think of as electrical pressure. In terms of orders of magnitude, just as comparison, your typical household outlet is nominally 120 volts. When we talk about transmission voltages, though, we're talking about 100,000 volts and above, typically. So that's 100 kV, 100 kilovolts. Most of the bulk grid around the United States is 230 kV and up, and you'll see voltages as high as 765 kV. Current is just the movement of charge through a conductor. And then power and energy, often we use those terms interchangeably. From a physics perspective, they're very different. You pay on your electric bill for energy. You don't pay for power. So you pay in terms of kilowatt hours. And typically in utilities, they measure it in terms of megawatt hours, in terms of the amount of power that's used or generated over a period of time. By and large, the bulk of the grid is alternating current, which means that every 60 seconds we go through a full cycle of positive and negative. So the voltage and the current alternate as a function of time. Direct current is akin to the current that you see out of your battery on your car. The batteries that power your cell phones, your computers, all those are direct current based, and you need rectification to get from AC to DC to power those. But we'll see in just a minute that as a function of technological history, that the grid evolved mostly as an AC grid. But there are times when DC makes sense to be used. And so the evolution goes back about a little bit over 100 years ago, what was deemed the War of the Currents. Thomas Edison and George Westinghouse were contemporaries. Edison and Westinghouse, they hated each other, and they fought vehemently for the technology they believed in. Edison was an astute businessman. He had a lot of patents in DC technology, was very politically savvy, pushed for DC being the technology of choice. Westinghouse, on the other hand, understood the benefits of AC, both from a technological convenience of running motors, because you had an alternating electromagnetic field associated with it, and the ability to change voltages. It was a very fierce political battle. Edison did things like fund the creation of the electric chair using alternating current to show the evils of alternating current versus direct current. He electrocuted Topsy the elephant. So if you go and you Google Topsy the elephant today, when you get back to your desk, you'll see some disturbing video footage of that from old Edison video footage. So what's a megawatt? A megawatt is a million watts. If you remember Back to the Future, a gigawatt would be a billion watts, right? Megawatts will power 10,100 megawatt light bulbs, just to give you a perspective, or powers about 800 average homes, or in hot areas like Houston and Phoenix, about 250 average homes. Our grid is composed of basically four main components. You start with the source, which is a generating station. You go through through transformation to the transmission grid. Typically, we think, as I mentioned before, the transmission grid is anything 100 kV and above. Standard voltages will range in the U.S. depending on standards that local utilities have adopted, but typically 138, 230, 345, and 500 kV are standard voltages. Then there's a distribution system that we'll talk about shortly, which is meant to directly serve customers. Larger industrial customers may connect directly to higher voltages, but then household kind of secondary customers that run off 120 volts or 240 volts nominally will be connected to slightly lower voltages.